Yeah, okay. So, good evening, everyone. Welcome to week 6 problem session of complexity theory. Okay. And this week's topic, okay, my name is again Bhavedeep Rai. Okay. This week's topic is randomized classes, intro to circuit complexity theory, and this Sipser's theorem, that is BPP is contained in sigma 2. Okay. So, before I move on to this week's questions, again, I would like to solve a few questions from the previous assignment. All right. So, from the previous assignment, I think one or two questions may be slightly trickier. So, I'll be looking at those, but I think the rest of the questions were fairly straightforward, and it was following almost directly from the definitions of RP, BPP, and so on. Okay. So here is one question. Okay. So the question says, consider a three-sat instance where each clause contains three distinct variables. Again, just to recall what is three-sat. Okay. Three-sat is a set of formula phi where phi is a 3 CNF and phi is satisfiable. And what is a 3 CNF? 3 CNF means that phi is of the form on the top you have an AND gate, on the bottom you have OR gates. Okay, and each of these OR gates are what are called clauses. So and each of the clauses have three inputs. And we already know what the complexity of 3-sat is. We already know that 3-sat is NP complete. I mean, solving, yeah, 3-sat is NP complete. So, question is, given we are given such a formula, okay, which is actually of very low depth, mind you, it's just the of depth 2. Checking satisfiability is so hard. Okay, so 3-sat is asking whether this formula is satisfiable or not. This 3 CNF is satisfiable or not. Okay, good. Now, they are saying each variable is independently and randomly assigned to true or false with equal probability. The expected fraction of clauses that are satisfied with this assignment is dash percentage. Okay, enter the answer in numerical form as accurately as possible. Okay, so here the algorithm. So they are what they are trying to do is they are trying to solve satisfiability using a randomized algorithm. Okay, so algorithm to solve SAT. This is what we are doing, and input is given a 3 CNF phi, and phi depends on inputs x1, x2, and so on till xn. And step 1 is uniformly and randomly, okay, choose some random bits r1, r2, and so on till rn. Okay. Okay, one more person is here. So I'll just repeat the question. The question is we have 3-sat here. We are trying to solve 3-sat, and the procedure is each variable is independently and randomly assigned true or false. So uniformly choose all the random bits. Now what do? We plug in these random bits into the 3 CNF. Okay. Evaluate phi on x1. Phi on inputs r1, r2, and so on till r. So this is what they are saying. And now at each point whether to set. So these are the variables that phi depends on. Whether to set x1 whether to set x1 um, to 0 or x1 to 1. This is, you're tossing a coin, right? So you're tossing a coin. So the probability of choosing whether, r1 should be set to 0 or r1 is set to 1 is half each. Okay, so each has a probability of half. By half probability it is 0, by half probability it is 1, and so on and so forth. Okay. Question says, now what is the question? The expected fraction of clauses that are satisfied with this assignment is, that is what it's saying. That is, so if you have these, this is my 3CNF. Okay, this is my 3CNF. Question is saying, how many of these clauses, or instead of even thinking about expected fraction, it's kind of saying that how many of these clauses are satisfied. Okay, that is what the question is saying. So here's the solution, or yeah, okay, I'll directly go on to the solution. Okay. So were any of you able to solve this problem? If so, we can ask the idea.
Okay, so since the Boolean formula is in the CNF form, so every clause must turn out to be a true value. And there are exact three Boolean literals in every clause. So what is the probability of having success? So that would be 1 minus the probability of getting a failure. So
1 minus?
1 minus the probability of getting a failure. So
Okay,
therefore,
yeah.
probability of getting a failure is so that all the three values comes out to be not true. I think so. So therefore, 1 minus 1 by 8. So that is what 7 by 8
Right.
thing. And then this thing should be true for every clause. So
Yeah.
so this would be so therefore I need, so each clause must be individually true. So therefore, if there are n number of the clauses, then I need to add this entire thing and say n number of the times probability of A1 union A2 and say union AN would be
Right.
equals to the probability summation of the how to will all the events be mutually exclusive? In that case, so I'll take the sum of this thing. I don't know.
Yeah, but that is very close. That is very close. It's at the end. Well, it's just about finding the average correctly, and that will follow. Yeah, good. Okay. So here's the idea. Okay. Um. Oh. Okay. So it's not. Okay. So here's the idea. So yeah, each of them. Okay. I want to ask how many clauses are satisfied. Okay. So probability that particular clause is satisfiable okay is yeah, probability that a particular clause is satisfiable. Let's try to calculate this. Okay, so what does a clause look like? Our clause is an or, not an and. A clause is an or of three inputs: x1, x2, x3, suppose, say, or x1, x2 bar, x3. Let's say this is the input. So in order to, for or to return false, okay, in order for or to return false, for example, for or to return true, either x1 should be 1 or x2 should be 0 or x3 should be 1, right? Because it's an or gate. Now, when and only when does or give a 0? Or will give a 0 when this is 0 and this is 0 and this is 0. All three of them are 0. So only or, okay, clause gives 0 only when x1 is 0, x2 is 1, x3 is 0. So only on this particular input does it give. So, and every gate has how many possible trees of inputs? Total number of inputs possible is equal to 2 to the 3, right? There are 2 to the 3 types of inputs I can feed to the OR gate, and only one of them, that is when I input 0 1 0, that is only when I get false. So which is 1 by 8. So sorry, not 1 by 8, this is 8. So probability that Ci is satisfiable is 1 minus probability that Ci is not satisfiable, and which is 1 minus, okay, the number of inputs which cause it to go to false, which is 1 input out of 8 inputs cause it to go to false, and then 7 by 8. Probability that Ci is satisfiable is 7 by 8. So a clause is very highly satisfiable in that sense. Okay. Yeah. Now, yeah. I think Goel also mentioned that now this clause has 7 by 8 probability of getting satisfied. This clause has 7 by 8 probability of getting satisfied, and so on and so forth. Now, question is how many fractions, what fraction of them will get satisfied, right? So we'll go on this way. Let's do it formally, okay? So suppose I'll define a random variable. Xi is a random variable that says 1 if clause Ci is satisfiable, okay, and 0 otherwise. Getting it? Now this is the random variable that says Ci is satisfied. Now what they are saying really is on average, okay, that's what they are asking, right? On average, what fraction and so on. Okay, on average, how many? So we want the expectation of the number of satisfiable clauses. Expectation on the number of satisfiable clauses. Okay, and what is the number of satisfiable clauses? Which is expectation on, by the way, the expectation is on, the random bits R, which is sampled from 0 1 to the n. Okay, on these inputs, and number of satisfiable clauses in phi. What are the number of satisfiable clauses in phi? They are nothing but the summation of xi, right? I goes from 1 to m, not m, n. Sorry, m. Suppose there are m clauses. Right? This is clear, right? So if you just sum, because the random variables are binary, okay, 0 and 1, just summing up all these random variables will exactly give me the number of clauses that are satisfied, because 1 means that a clause is satisfiable. Okay, I want the expected value of this. Now what can I use? I can use what is called linearity of expectation. Okay, the linearity of expectation, I think you've seen it in the lectures probably. Linearity of expectation, summing up of average, in other words, is that expectation of A plus B equals expectation of A plus expectation of B. So I can do that. Since this is a summation inside, I can bring the summation outside. Instead of expectation of sums, I can make it sums of expectations. Okay, sum of expectation over xi. Getting it? So now we have transformed this problem by linearity of expectation. Okay, now xi, yeah, expectation of xi. Now what is, now you must have seen another in the lecture, that expectation of xi equals, you can write it in terms of probabilities, that is xi times probability that, sorry, yeah, you can write it as summation of xi probability of xi, which is so here it will be xi has values either 0 or 1, so you can write it as probability of xi equals 1 times 1 plus probability of xi equals 0 times 0. But this thing is 0 anyway. So you have probability of xi equals 1. And oh, okay. And this is a summation, right? Over 1 to m. And this is again summation over I equals 1 to m, probability that xi equals 1. Right? Now this is 1. Now you are just summing it up. Okay. So you are just summing it up, and therefore this summation, since my answer finally, therefore this summation will just be m times probability of xi equals 1, right? Because I'm doing it m many times. Okay. And now, so sorry, but this. Now, what is probability that xi is 1? Each of the clauses can be satisfied by 7 by 8 probability. So summation I equals 1 to m 7 by 8. Now you do, what does this mean? You do 7 by 8 plus 7 by 8 plus 7 by 8 and so on, m times. M times. Which is nothing but m times 7 by 8. Right? So this is the, okay, this is expected number of clauses satisfied. What do we need? We need expected fraction of clauses. We need expected fraction of clauses, and so total number of clauses equals m. So therefore expected fraction equals m times 7 by 8 divided by m, which is the total, which is 7 by 8. Okay. And so which is some, I think, 0.875 or something like this, which is 87.5. Okay. So that's percent. So that is one way to obtain the answer.
Yes, but this percentage is quite high.
Yeah, this percentage is quite high, and it is not asking whether the final output is what is the probability that the entire circuit will actually give a 1. It is asking how many clauses can be satisfied. So yeah, the probability is quite high. So you can say for most circuits, because most circuits will have a combination of these clauses. Okay, you can say for most circuits, this kind of strategy will give you the correct answer with some high probability. But yeah, it is true that most of the clauses will be satisfied using this. That's right. That's right.
Yes.
Okay. But internally, what you said in the beginning is happening, that each of the clauses have 7 by 8 probability. Now you are summing up overall probabilities, right? So either the probability that this clause is satisfied or this clause is satisfied and so on, and then we are using this expectation formula to finally get the answer, right? Okay.
Yes.
So okay, this is the first thing. Now let's look at this. Okay. The question is saying, suppose x1 and x2 are independent and identically distributed random variables such that xi equals 0 is 0.2 and xi equals 1 is 0.8. Okay. Compute the probability that p x1 plus x2 is greater than or equal to 1. Enter the answer in numerals. I think you may have been able to do this. Okay. and I'll just quickly show it to you. It's not very difficult. So xi and x1 and x2 are independently and identically distributed random variables. The fact that they are independent is important. Okay, and now probability that xi equals 0 equals 0.2 for both I equals 1 and 2. Okay, meaning probability that x1 is 0 is 0.2, as well as probability of x2 is 0 is 0.2. And so it follows that probability that x1 is 1 is 0.8, since they are identically distributed. X2 is 1 is equal to 0.8, and also by the definition they give here. Okay, so this is what we have. They are asking to compute the probability that P of compute probability of x1 plus x2 is at least 1. This is what they are asking. Now x1 and x2 are random variables, but they are binary, boolean. They can either be 0 or 1. Okay, now they are asking, if we take this two random variables and then sum them up, what is the probability that they are at least 1? Okay, so or in other words, I can write it as 1 minus probability that the sum of x1 plus x2 is strictly less than 1. Right, now, but x1 x2 are but x1 plus x2 will also belong to 0 or 1, right? Because both of them are belonging to 0 1, so it cannot be that they are lying somewhere between 0 and 1. Okay, so the addition will also give us a binary number. So this means that this value is nothing but 1 minus probability of x1 plus x2 equals 0, because strictly less than 1 would mean that it is equal to 0. Now that we have this, I sum them up. Okay, so now probability that x1 plus x2 is equal to 0. Right, now for this to happen, what do you need? For this to happen, both x1 should be 0 and x2 should be 0. And what are the total number of outcomes?
This is 0.4.
It is 0.4.
Yes, the probability of that x1 plus.
Why is it 0.4?
Because both the events are independent of each other. So therefore, x1 plus x2 is equal to 0 means x1 is 0 as well as x2 is 0.
Right.
Therefore, the probability of both becoming 0 is equal to the 0.2 multiplied by 0.2.
Yeah, so it's not 0.4, it is 0.2 times 0.2 is
0.04.
0.04. Right.
Yeah.
Okay. Good. Yeah. So now both are independent random variables. So we know in case of independent events in probability, we can multiply them, their probability separately. Right. So this is because x1 and x2 are independent, which is 1 minus. So what is the probability that x1 is 0? It is 1 by sorry, the probability that x1 is 0 is 0.2, probability that x2 is 0 is 0.2. So 0.2 times 0.2, which is equal to 1 minus 0.04, which is equal to 0.96, is your answer. Okay, so is this clear, Goel, Suraj? Yeah. Okay, Suraj?
Yes.
Yeah, okay, good. So yeah, the questions were fairly easy. Maybe the previous one was a bit needed a bit thought, but yeah, that is all I would like to discuss from the previous assignment. Okay. Yeah. Now let's move to this week's content, and as requested, I'll be continuing. Oh, okay. I'll be continuing last time's question. Okay. On because this week also handles on de-randomization only, so it still makes sense to discuss. Sorry, not de-randomization, randomization makes sense to discuss randomization. Okay, so yeah, question is as follows. Oh, okay. So before I move on, let us. I want to do this again. Let us create the landscape of complexity classes once again. Okay, so here you have L, here you have NL. NL is contained in P, we know, and P is contained in NP and then what else did we have? Uh, we had RP, right? RP is contained in NP, and RP and co-RP together contain ZPP, and ZPP also contain P, and NP itself is contained in um, P space, which is contained in EXP. And any other classes are there? Is equal to NP space.
What about BPP here?
Yeah, good question. Where should BPP sit here? Yeah.
So where should we place BPP? So BPP is
Huh. Okay, let's see. Will BPP contain P?
no, no.
So, yeah.
So BPP in BPP, the probability of getting all the strings which are the part of the language are getting accepted with the probability of greater than or equals to 2/3.
Yeah.
All the strings which are not the part of the language are getting still getting accepted with the probability of 1/3.
Huh.
And in case of P, all the strings which are the part of the language are getting accepted with the probability of 1,
Right, 1.
part with the probability of 0.
0.
So therefore, this P won't be there. I mean, in a subset of the BPP.
Okay, Suraj says at top above NEXP. Okay. Above NEXP. Okay. And Goel, you are saying that BPP should not contain P.
Yes.
But the reason that you give me exactly tells that it should contain P, right? Because isn't every P algorithm a BPP algorithm also? Because BPP says if X is in L, then probability of accepting is greater than 2/3, and X is not in L, then the probability of rejecting is less than 1/3. Right?
Yes.
Oh, sorry, is at least 2/3 again rejecting. If I write it as accepting, then the probability of accepting is less than 1/3.
Yes.
Right. Now, what is P? P is X is in L, then probability of accepting is 1, which is greater than 2/3. And X is not in L, then the probability that it accepts is 0, which is less than 1/3.
This P would be there in BPP.
P would be there in BPP. That's right.
Yes.
Because every P algorithm, if I give you a P algorithm, it still satisfies this. So every P algorithm is still a BPP algorithm.
Yes.
Right. But is every BPP a P algorithm? That is another question. So, okay. So, is that clear, Suraj, also? So, oh, yeah. But, Suraj, you... Okay, you are saying it's above NEXP, no? Or you said below. Okay, at top above NEXP. Okay. So is it clear, Suraj? So BPP is here. Let's say. Now, I think you've. In fact, this is argument to show that P is contained in BPP. Now, look at RP's conditions also. RP is one-sided error. You can do a similar thing. You can do a similar analysis and see that, oh, RP's parameters also satisfy BPP's parameter. So every RP algorithm is also a BPP algorithm. Okay? Yeah. Okay. So BPP is situated somewhere here. And now, okay, BPP versus NP. Okay, this is interesting. We'll talk about it. Um, Now, is there any upper bound? So that is, can you tell what BPP is contained in? What is the best containment you can give? Is BPP contained in NP or P space or EXP or NEXP?
So certainly BPP would be contained in P space. There is no doubt in this.
Okay.
And we do not know relationship in between BPP and NP because of the way we have defined BPP. So there are gaps because in NP all the strings which are the part of the language are getting accepted with the priority
Hmm.
100, and strings which are not the part of the language are getting accepted with the priority of 0. So there are gaps, yes, in between this 2/3 and 1/3.
Yeah.
So we do not know relationship in between BPP and NP. However, this BPP would be there in P space.
Yeah. Good. So yeah, there is no, you cannot fit it directly with the definition, and BPP is contained in P space, right? So can you now tell me, can you fit a class in between that is contained in P space and it contains BPP? It is not written here. The class is not here, but you've seen the class extensively before, and this was proved in the lectures for this. Um, this week.
So yes, if it is polynomial hierarchy theory, uh, NP is if NP is sigma 1, uh, and so for I mean I don't know, but probably higher than sigma 1 can be included or something like that.
So NP is in sigma 1, and
Yes,
polynomial hierarchy, it's contained in P space, right?
yes.
Yes. Because we saw that TQBF, right? Totally quantified Boolean formula, which is P space complete. It can actually solve polynomial hierarchy. And PH contains BPP. Why does PH contain BPP? I mean, what theorem is it? It's the Sipser. Okay, I forgot the middle guy's name. Lautenman theorem. So this was done. This was one of the topics in this week's content, right? So pH contains BPP, and that's all. Okay. Now, um, now question is like how powerful is BPP is always a huge question, because finally we want to get rid of randomness and find deterministic algorithms, right? So BPP versus P question is a huge question. Question is a huge question. So this question addresses the problem of de-randomization. If you prove that BPP contains P contains BPP, that is BPP equals P, then you prove that every randomized algorithm can be de-randomized and made deterministic. So which has not been proved yet, but the common belief is that BPP is equal to P. That is a common belief right now, but we don't have a proof for that. Yeah.
So, what is the intuition behind this belief that every randomization can be de-randomized?
Yeah. So there are a number of reasons. Firstly, there are some theorems that. So firstly, we have that P is not equal to NP is what is the belief is, right?
Yes.
And if it is shown that BPP is actually equal to NP, then, and assuming this, it means that BPP is not equal to NP. Sorry, BPP is not equal to P. Yeah, BPP is not equal to P, right?
Yes.
So, um, okay. So this is not the reason. Okay, wait. This, in fact, one example I can give you is one of the questions that I have given you. People's happy. No, even this is not directly. Okay, but I'll give you a slightly more advanced reason. Okay, so there is a topic, okay, which is a hot topic right now, which is called hardness versus randomness. Okay, I'm going a bit off out of scope, but hardness versus randomness simply means that um, if you can find hard problems, if hard functions exist, then you can do de-randomization. Okay, if hard problems exist, then you can do perform de-randomization. And if you can do de-randomization, then existence of hard problems is difficult. Okay, so if you so showing BPP is equal to P is akin to showing that de-randomization is possible. And if you show that de-randomization is possible, okay, then you show that certain kind of hard problems do not exist, which is the common belief. But I'm being very high level out here, okay. But you can explore this concept, hardness versus randomness concept, and but it is not immediate to my mind right now. But there are actually simpler reasons why PPP can be equal to P. There are simple theorems to actually demonstrate this. Uh, um, Let me think that if
Actually, BPP is not equals to P makes sense. I mean, following the common sense, and implying that randomization is really powerful. That using randomization, say we can solve some of the problems.
yeah, but we cannot always say that, right? I mean that. I mean, because see, it may be so that de-randomization is always possible, because otherwise we would not even address this particular question about de-randomizing algorithms. For example, I'll give you an example that non-determinism, it makes sense. I mean, using the same argument, it makes sense that non-determinism is more powerful than determinism, right?
Yes.
So this intuition can be weakly used to say that okay, maybe P is not equal to NP. That's why.
Yes.
But to shatter this concept, think about the um, think about non-determinism in terms of space. Okay, in terms of space, if you go higher above to NP space and anything above it, non-determinism does not make sense. I mean, non-determinism is the same. It does
Yes.
not give more power.
Yes. Yes. Space wise, it does not give more power.
Yeah. So I mean, it may not be that straightforward that randomization always. Definitely, there is an advantage to randomization. That is, we can build algorithms. Uh, I mean, we can build algorithms in a more natural way, and we can build algorithms for which we don't know deterministic algorithms. But And it makes sense also. Randomness intuitively gives us more power, but we cannot say for sure that is there.
Yes.
And actually, there is another reason, but I don't want to spoil this course for you by saying, I'll just, there is a class called P/Poly, okay? There's a class called P/Poly. This is related to circuits and advice and so on. If you've seen if you've started seeing this week's lecture, good enough. Well, this contains BPP, and this P/Poly contains BPP, okay? And P/Poly is very much related to P. It is in terms of what is called uniformity. Okay, in terms of Turing machines, P/Poly are very close. Okay, and since BPP is contained in P/Poly, and it is not known that NP is contained in P/Poly, which we don't believe so. Okay, because if you prove that NP is contained in P/Poly, you will end up proving that P is not equal to NP. Sorry, P equals NP. If you show that NP is contained in P/Poly. So I'll explain this very much properly in the next week why this happens, but I don't want to spoil this week's content. For you guys. So that is one of the reasons why actually PPP is set to be equal to P.
Yes. Yes.
Okay, so in your free time, maybe you can explore this. So you can check out if BPP, not BPP, and P is contained in P/Poly, then P equals P. And so on. And you can go across several theorems and so on, which will actually strengthen their hope that BPP is actually more equal to P.
Yes. And in this diagram, probably you have mistakenly drawn an edge in between RP and BPP, or is this the reality that probably you were trying to draw an edge in between P and BPP?
You mean this line?
Yes, yes. Is this correct, or you wanted to draw an edge in between P and BPP?
No. This is correct, isn't it?
But this RP is there in BPP. Is this okay?
So RP's definition is what? It has one-sided error. The other side it has zero. So any RP algorithm is also a BPP algorithm, right?
Yes. So can we draw another edge in between, say, from P to BPP here in this?
Oh, okay. So this diagram is transitive. This containment diagram is transitive. So it means if you got it. So
Okay.
if right. So it means BPP is contained. P is contained in BPP also. Because if I draw lines, then there will be too many lines. Because then there will be lines across any XP also.
Yes.
Yeah, okay. Good. So yeah, now that we have the picture. Anyway, so let's now an interesting thing. Okay. What about randomization in space? Now we talk about something called BPL. Okay. So BPL. So where is BPL exactly? And the claim is that BPL is contained in P. Right. So this is what we want to show. Okay. So right. Okay. So define BPL to be the class of languages accepted by probabilistic log space Turing machines with bounded error. Show that BPL is contained in P. Okay. And I remember last time I told you I asked you what happens when you square an adjacency matrix, right? I asked you, so if A is an adjacency matrix of G, and I asked you A square, what does it represent? It represented can I reach from U to V in 2 steps. This one is reach in 1 step. And A cube, and I keep doing this and I do A to the n, then it means can I reach from U to V in n steps. Last time I had asked you to check it out, okay? And the intuition is again that if I have UV here and I say, so if it means if this is my adjacency matrix A, then it means that I can reach from U to V in one step if there is a 1 here. And if there is a 1 here. And I will multiply this to a column here, right? And when I do the multiplication, okay, and so if it so happens that V is here and there is a W here, so it means I can reach from V to W in one step. And when these two, the row and the column will match up, right? The row and the column will match up. So what I get is a resulting U versus a W. If it shows a 1, then it means U to W in 2 steps. So that is what A square is. Okay, so that is the general idea. I hope this is clear. Now we want to extend this idea, okay? And see, this is one way of showing reachability, if you can see. And this shows path n, that is path k, can be written as GST S can reach T in k steps. So this is what this is, right? And question is, okay, one nice idea is whether you can. This is one of the questions in this problem solving session also. I'll come to it. Can you solve reachability using this? Okay. Actually, using this idea, you can find an alternate proof to Savage's theorem, which is quite simple also. It's not very difficult. Okay. Yeah, let's move on. Now that is what we have, right? Now think of the configuration graph. Last time I had come to this also. Now think of the configuration graph of the BPL machine. Okay. So what will the configuration graph have? What does a configuration look like in any machine? In any machine, a configuration looks as follows. You have the current state of the machine. You have the work tape content. Okay. And you finally have the head position of the Turing machine. Okay. And how many number of configurations are possible? Is the number of states, which is constant, times the work tape content, number of configuration for BPL machine, times the work tape content, which is which is 2 to the possible contents in the work tape, right? Because my symbols are binary. So 2 to the, what is the space given for a BPL machine? It's a log space machine. So 2 to the order log n times head position, which is there are log n many cells, and to index to each of them, I need log of log n. So which is, so 2 to the log n is some polynomial, which is still polynomial. So this is also within polynomial. So this is some poly n size configuration graph. So now think of it as a graph. Think of each configuration as a graph. Configuration graph. Think of each configuration as a graph.
Actually, this calculation is not clear. So can you explain this calculation again? Why this? I can understand that we are using BPL, and BPL stands for that the BPL, the BPP machine, but then occupying logarithmic space.
Right. Until now, the same analysis can hold for NL also and L also.
Yes, yes. So state is of the order of one. We have finite number of the states.
Right.
The work tape content is 2 raised to the power of the order of log n. Why so? Because for every cell we have got two possibilities, and for log n number
Yeah,
of the we have
exactly.
our log n number of the possibilities. And what about this head position? So since machine is occupying the logarithmic number of the space, so to count
Huh,
the
huh.
log number of the positions, we require this log of log n thing. Is this
Exactly, exactly. So there are log n many cells, okay,
yes,
to
yes,
index into a cell, okay, and to number it, okay,
yes,
right. So I'll need log of log n.
log of log n. So how this quantity came out to be this the poly of n?
So it is some polynomial. I'm not specifying what the polynomial is
But
because
how will this be a
how did it come? Because see, I have order one which is very small times 2 to the log n is 2 to the n to the c. Sorry, 2 to the c log n, right?
yes,
Times log n. And this I can write it as order 1 times 2 to the log n whole to the c times log n. And 2 to the log n whole to the c. What is 2 to the log n? It is n by property of log. Right?
yes.
So this is nothing but polynomial.
Oh, assuming that log of n is what I mean.
Log of log n is very small because log n is already very small.
Yes,
Okay?
yes,
Log n is a very small quantity. It grows, I mean, it grows slower than the log function. Log.
so what? So then, what this term is that log n raised to the power 4, say log 4 and then n. So what this quantity is?
I did not understand what.
So what this quantity is log n raised to the power 4, and then which we used to write as log uh, power 4.
Oh, okay. So log n raised to the power 4 is log n times log n and so on 4 times. But log what we are saying is log n. So first you compute this, then you perform log of this, then you perform log of this. This is
Okay.
larger than log n. Well, this is smaller than log n. Getting it?
Oh, yes, yes, yes.
Okay. So yeah. Okay, I think I made a small mistake here. I don't think, I think to index it you'll require log n bits only. Exactly. Yeah. Suraj, I think log n is not actually correct. It's just log n. Because while counting, you'll require exactly 1 to log n many. Right?
Yes, but then the space occupied is log n only. So
Yeah, then the
therefore,
space, yeah.
I would be counting a quantity log n, and to index log n quantity, I would be requiring log of log n thing. Say if I want to count n numbers, then I would be requiring say log n
Right.
number of the bits. So, but if I want to count say log n number of the things, then I would be requiring log of log n number of.
Um, yeah, that's right. Sorry. That's right. Yeah, Suraj, you're saying 2 to the log n. Why is the 2 there? Um, right. That's right. Sorry. Yeah, now you need to do the same thing here also. Like if you maintain like a cell, okay, which a set of cell which contains the counter, okay, how many possibilities are there for the count? Firstly, this cell should be log n length, right? And there are two choices for each of these. So 2 to the log n, which is 2 to the which is log n. That's right. So this is 2 to the log n. right? Correct, right?
Yes. So, say regarding this head position, so why to take the 2 raised to the power log of log n?
Yeah, because we are trying to find out the number of possible head positions.
So, like the RW head of the Turing machine may point to any one of the log n number of the possibilities, and that's it. So, it's okay that we consider the content. As far as the content is fine, then we can raise this 2 raised to the power order of log n, because for each cell we have got two possibilities.
Yeah.
But as far as the position of the head is position of the reading writing head is concerned, so the reading writing head can point to one out of the log n number of the possibilities.
That's right. That's right.
It would be equals to the log of log n thing, and there is no need to take this 2 raised to the power the log of log n number of the things. So yeah.
Well, log n is actually not the different numbers of head positions, right? Log n is the space required to store the different number of head positions. Right? Well,
Yes. Yes. So say yeah, but
but we are
yes.
trying to count the number of configurations, not the space occupied on storing.
Mhm. No, but still, I believe that this head position is safe. Like, I mean, how many different configurations are possible for a Turing machine? So we used to write it as a Pn. Say, for a Turing machine bounded by the space of the order of Pn. So then we write Pn and give Pn number of the possibilities. So head may point to one out of the Pn number of the possibilities,
Right,
multiplied
right,
by wherein S is the number of the states, multiplied by t raised to the power t raised to the power n, wherein t is the number of cardinality of the set of the date symbols.
right,
So I mean, in this way we derive this, we solve the Sebis theorem, etc.
right.
So head position is actually the RW head may point to one out of how many number of the cells.
Yeah, one out of log n many cells.
So there are how many number of the cells are there? There are log n number of the cells.
Right, that's correct.
Yes. So instead of 2 raised to the power log of n thing, it should be simply log n, I think.
Yeah, that's right. It can be interpreted in both ways. That's right.
Yes, yes. So now it's clear that instead of log n, it should be simple plain log n.
Yeah, it can be simply log n or c log n or something like that.
Yes, yes.
Okay, right. Okay, now let's look at the configuration. Okay, so now think of each configuration graph. Now think of each of these, strings. Okay, each of these strings of length, polynomial length. Okay, which is some polynomial length. Okay, each of these strings are some configurations, possible configuration of the machine on the input x. Okay, and now they can move from one configuration to another. We know that this, so a similar kind of technique was used to show that L is contained in P, remember? But remember, to show L is contained in P, we had the observation that you cannot have cycles. You cannot have directed cycles. For example, you cannot have this. Something like this was not allowed in L is contained in P in the configuration graph. Because if you had this, then you are locked in this loop forever and your machine will never halt. And since we are talking about an L machine, it is decidable, so it should be halting. So, but in the case of non-determinism or randomness, this is allowed. Cycles are allowed. Why? Because I am allowing randomness. So if I am allowing randomness, it may be so that on particular coin toss I'm taking a certain path, and on another coin toss I'm not taking a path. So this is allowed. Yeah, right. So if there is a cycle like this, so it may be so that if I do a coin toss and I go take a 0, then I go here. And if I do a coin toss, then I take Okay, so not this, then I go somewhere else. So since randomization is allowed, so I can allow cycles to happen. Okay, so this, it cannot directly imply that BPL is contained in P. I need to do something more interesting. But now see, the fact that I can move from, and I can move, if I toss a coin, okay, and then I go to this configuration. If I go toss another coin, I go to this. If I get heads, I'll go to this. If I get tails, I'll go to this, and so on and so forth. Right. The probability of moving from one configuration to another configuration is half. Right. That's right. Right. So if probability, okay, I'll write it again. A, B, C, B. Okay. Probability that I can move from A to B is half. Probability that I can move from configuration A to C is also half. Right. And the probability that I can go from A to D in one step is 0. Right? In one step, all of this.
Yes.
Right. So, yeah. Now, consider the adjacency matrix of this graph, okay, of this configuration graph. Consider the adjacency matrix configuration graph G. Let me call it matrix A. Consider it to be like this. Now, what does the adjacency matrix look like? 0, 0, 1, 0, 1, and so on. And so on, so on. What does this represent? In one step, I can go to from one configuration to another. This is what it represents, right? Instead of now, what I'll do is replace ones by half. Okay. So what will I do? If I see a if I see a 1, I'll convert it to half. Since I'm assuming that I'm tossing exactly one coin on the way. Okay. Okay. And so on. I'll do this.
Yes.
So now this matrix becomes transformed into a matrix that says, in one step, what is the probability that I can move from A to B? In one step, what is the probability that I can move from A to B? This is what it is showing. Okay.
Yes.
Now let's see. Okay. This is the okay. Now let's apply the same technique of multiplying here. Okay. A, B, C, D. So A, B, C, B. So let's make its probability matrix. Okay. And okay, let's make an E also. Okay, let's make a matrix like this. A, B, C, D, E, A, B, C, D, E. Okay. Now, so what is connected? A is connected to BC, so half half. B is connected to, let's say, on 0, no. B is connected to E and D. B is connected to E and D. Okay. And rest are zeros. And observe that, when you sum up the rows and columns, you will get 1 because they are probabilities. So this is what is called a stochastic matrix in statistics. Okay. and C is connected to D. C is connected to D. Okay, and okay, C is connected to D using.
But I have a question here.
Yeah.
This is not necessary that from the configuration A I can only move to the only to exact two configurations.
Yeah.
So I
So
can make it to more than two configurations. In that case, the sum will not come out to be one.
yeah. So but remember we are. So you mean if you toss more than one coin,
Yes, yes.
right? But I can always split that into this particular setting. In that case, I'll accordingly scale it. Instead, if I toss 4 coins, then I'll do 1/4. Okay, but the
Mm.
argument will still hold. Still hold.
Oh,
Okay,
okay, okay.
and okay, C is connected to D. For example, C is connected to D with a probability 1, right? So I can write 1 here, and if the argument will still hold. Okay, and but for now we are assuming without loss of generality that we are moving to two states. It simplifies the calculations, and D moves to nothing, and B moves to E and D. Sorry, E moves to nothing. Okay, now this is my matrix. Let me shift this a bit here, and let me copy and okay. Let me duplicate and bring it here, and I'm multiplying this, and I'm naming it E square. Let's see what happens. Okay, and first A B C D E, A B C D E. Okay, and let's see what happens when I multiply them. So the first location A 0 0, everything will add to 0 because we are multiplying with a 0 column and 0. And let's multiply this and this, so nothing matches up, 0. Let's multiply this and this. Okay, nothing again matches up, so 0, right? Now let's multiply this and this. Okay, so half multiplies with half to form half, and half multiplies with 1 to form 1. Okay, so this is half times half, that is 1/4, times plus, I'll do it with another color, 1/4 plus 1 times half, right, which is half. Okay, and finally this multiplied with this will be 1/4. Okay, and now what? Let's do the next column just for clarity's sake. That if I do B times this, I'll get 0. Now if I do B times this, I'll get 0 again. If I do B times this, again I'll get 0. And now I do B times D, I again get 0. Now if I do B times this, okay, again I get 0. Nothing. But anyway, I think even this is enough for our analysis. So what do we get here? A to D, what am I getting? 1/4 plus half. 1/4 plus half. And A to E, what I'm getting? 1/4. And what is the probability? Now I ask you, okay, probability of moving from A to D in two steps. From moving A to D in two steps.
3 by 4.
Yeah, right. Will be exactly equal to 3 by 4. Why? Because um, A to D is nothing but the probability of moving from A to B and then to D. So that is some half probability and half probability, and from here half probability and one probability. Or in other words, I can also see it in the number of ways, of moving in from A to D. Okay, there are a total of 4 routes in 2 steps. But we are assuming that it's a binary. If it was like this, then there are a total of 4 routes because we are tossing 2 coins on each way, and out of which 3 routes will actually lead to D, and that is another way in which we are seeing. Okay, this is 3 by 4, and here too what we obtain 3 by 4. And again, probability of moving from A to E, now this is simple, is what? So from here definitely, from here with half probability I can move to B, right? That is probability on moving from A to B times probability that B moves to E, since they are independent events. Okay, and so what is it? Probability that A moves to B is half times B moves to E is again half, which is 1 by 4. So do you see now that A square says probability, okay, that A goes to B in 2 steps, right?
Yes.
Now what is A to the K? That is probability that A goes to B in K steps. Okay. Now let's see it as a machine, because this is a configuration. Okay. So A to the K, okay, is represents the probability, okay, that configuration I goes to configuration J in K steps. Now can you guess what our algorithm is? How many steps do we need here? Okay, what configuration, what special configuration in the graph are we interested in?
So I could not understand this question, but so the thing is that there are k minus 1 number of the configurations in between. Say in between the configuration I and the configuration J, there would be k minus 1 number of the configurations in between.
Yeah, that is fine. But what I'm asking is, see, we want to now. Okay, we want to simulate the BPP algorithm. Okay,
Yes.
on that particular input. What is the definition of BPP? The probability on accepting should be,
Yes, should be greater than or equals to 2/3.
yeah. Now the keyword is accepting here.
Yes.
So what kind of configuration in the graph? What kind of node are we interested in reaching?
Yes. So we are interested in reaching the accepting configuration.
Exactly.
So then if accepting configuration is k steps away from the initial configuration, it should be reachable from the configuration I to the configuration J in maximum, say with the probability of greater than 2/3. It should be reachable.
Exactly.
That's simulating BPP. And but how does this violate this thing? Because just now we have seen that if we consider one configuration in between, and the
Hmm.
probability came out to be what? 3, 4, to the level
Hmm.
of 3.
Right, right, right,
So yes, yes.
right. So I'll write it formally. Okay, you can see. Okay. So I'll call it now let's say, suppose, okay, the BPL algorithm, okay, um, is A. Okay, not A, I think. So M. BPP algorithm is M. Okay. So here is a P algorithm to simulate M. Okay, and on input I have X. Now what do you do here? What do you do? First step is build my configuration graph. I can do that easily by looking, because the size of the configuration graph is size of config graph is polynomial. I can do that in polynomial type. Okay, looking at machine. Okay, M. Let me call this new algorithm M prime. Okay, machine M on input X. I can track it and so on. Okay, and then make the entire configuration graph. Now what I'll do is, suppose the BPL algorithm is M and it runs in time n to the C. Then what do I do? Compute and let me uh, and okay, configuration graph G. Okay, compute the n to the cth power of the adjacency matrix of the graph. It means in n to the c steps, what is the probability that I reach from this state to that state and so on? In n to the c steps. Okay, and then check. So let's say, suppose start state is S and accepting state, not state, start configuration is S and accepting configuration. Actually, there could be multiple accepting configuration, but it's only a matter of adding the probabilities. So accepting configurations is T. Check if that adjacency matrix at G to the n to the C, okay, at position S comma T is greater than or equal to 3/4. If yes, accept. Otherwise, reject. Correct? So what does it mean? Why are we doing this? Because in n to the C steps, if the machine were to be accepting and I'm tossing the coins uniformly at random, okay, then with a probability over the tossing of coins, I would be reaching at a with a the accepting state with a probability of at least 3/4 if X was good for us, right? And I'm accounting for all the tossing coins, right? When we are assuming that the distribution is uniformly at random, it's a uniform distribution. So the finally we compute the final probability and the final probabilities and check whether the start state to the configuration state in the adjacency graph in n to the c steps is it still 3/4. If it is, then I'll accept. Otherwise, I'll reject. Is that clear?
Yes, but then, yeah, I was thinking that this entire argument is true, but why this entire argument is true for BPL only and not for BPP or anything else?
Ha, nice. Okay, good question. Okay. I'll give you. Suraj, can you attempt to answer that? Why does this work only for PPL, not for PPP?
So I
Okay,
think
I'll give you a hint. Okay, L is contained in P, right? L is contained in P, right? Can and you remember the argument for it? We looked at the configuration graph and then saw that there are not many configurations. Can we use the same algorithm to show that P space is in P?
no, no,
No.
we can.
Why?
No, we cannot because there could be exponentially large number of the configurations possible, contrary to this case wherein we have only polynomial number of.
Exactly. Exactly. In the case of BPP, there is the state which takes order one, and there is a huge polynomial space it may take, and then head position.
Yes, yes, yes.
And accounting for this, it would be 2 to the log, 2 to the polynomial. So we cannot use
Yes.
this approach. The number of configurations will be too large, it will be exponential. So we
Yeah.
cannot use this to show BPP is contained in P. But we can use this to show that PPL is contained. Okay?
Yes. Yes.
So this is a nice way to actually use a probabilistic argument to actually show the containment. Okay? Yeah. Is this clear, both of you? Okay. Suraj?
Yes, sir.
Okay, good. So, okay, I'm coming back. Can you have a look at this question? I'll be back in a minute. Have a look at this question. Try to think about a solution. Yeah. So, any thoughts?
Yes. So if P is equal to NP, and so yes, it's true that since that is NP complete, so it would be solvable in the polynomial time.
Hmm.
And so as far as for this MP class is concerned, so Turing machine works in two phases. It guesses, it makes a guess, and then it's verified. So since P is equal to MP, so now this at the most Turing machine would be making this non-deterministic Turing machine would be making a polynomial number of the guesses to know that whether the value of this variable should be a true or should be a false.
Well, by definition of NP, it can only make polynomial number of guesses, right? Because non-deterministically, it still requires polynomial.
Yes, non-deterministically it will find that whether this solution is better than the other solutions or not.
This solution is better than the other solution. Okay, continue.
So like say if we have got n number of the Boolean literals, the total number of the possibilities will be 2 raised to the power n.
Right.
But then if we use say okay, so if we use non-determinism, then we would be having a polynomial number of the guesses.
But we are not allowed to use non-determinism directly. We still want a deterministic algorithm. You get it? What I'm saying?
Probably not.
I got what you are trying to say. You are saying that since P equals NP, non-determinism is given for free to us. That's what you mean, no?
Yes.
And I'll use non-determinism in my algorithm. That's what you're saying. But that is not what. But as soon as you use non-determinism algorithm, your algorithm becomes your algorithm is an NP algorithm.
Yes, so my algorithm is NP because then so I view non-determinism as a guiding factor. So non-determinism would be able to then tell me that okay, this solution is better than the other solution. You need not to explore 2 raised to the power n number of the possibilities. I give you one solution, and this solution is better than other solutions, and then I can verify whether this indeed is a valid solution or not in the polynomial amount of the time. So in that guessing phase, wherein I would be requiring exponentially large number of the possibilities, with the help of determinism now, I would be able to, at the most, I need to explore polynomially large number of the possibilities. That's it. And
but that I'm not understanding how you're only exploring polynomial number of.
Okay, so it is like this, say, like in this set problem. So now non-determinism will guide me that okay, this is better that instead of taking this assignment, you go for this assignment.
Yeah.
So non-determinism probably would be able to generate such an assignment, won't take more than polynomial amount of the time. This is the assumption. Because we are working with a very, very powerful machine and it is non-deterministic and won't be taking exponential amount of the time to generate a right guess. And so at the most, it can take a polynomial amount of the time. And verification further would require the polynomial amount of the time. So therefore, yes, finding a satisfying assignment can also be done.
Yeah. But I get it why you are saying this. But here's okay. So what I have is okay. What is my? I think my it has charge. So if P equals NP, then there exists a deterministic Turing machine. Okay, deterministic Turing machine M solving set. This is what they are saying. This is what we are saying. Okay. Now what we want is we don't want a yes or no answer now. Okay. We don't want a decision. There's not a decision problem anymore. This is what is called a search problem. We need to find a satisfying assignment. I get it what you're saying. The fact that a non-deterministic machine actually is capable of exploring several certificates at once and finding that assignment that will satisfy the phi, and this is all we need. That's what you're saying, right? Well.
Yes, and I view it as the part of the definition of the non-determinism.
This is the definition of non-determinism that we are working with, and yeah, that is fine. This I completely agree. But what we want is we want uh, a deterministic algorithm that finds satisfying assignment. Now, if you say, okay, we'll use the same thing to actually do here, but that is not what P equals NP is implying, right? P is equal to NP is implying that there is a deterministic Turing machine that solves satisfiability. That is all the guarantee that it is giving. Furthermore, it may not be that the deterministic simulation is working in this way only. The deterministic Turing machine is exploring all paths and so on. It may be some other very strange technique that it is doing this. Right. So this is the only guarantee that P is equal to NP is giving to us. Not the guarantee that a deterministic machine will be able to explore all paths. And that too non-deterministically, which is not clear to us how that can be done by a deterministic machine at all. Is Suraj is saying we can put value in variable and run P algo for SAT and check that value can lead to satisfying assignment or not. If yes, then we'll put another value in second variable and repeat n times for n variables. Yeah, that is the correct answer. Okay. Yeah. Goel, is that clear what I'm saying?
No, it is not clear to me.
Okay. So here's what. But I want to hear from you again. Okay. So describe to me step by step what will your P algorithm do to solve SAT. You are given a formula.
Yes, so formula is given. So my algorithm will generate one assignment.
Okay, it will generate one assignment. Okay, okay.
And for that one assignment, I will check that whether the set instance is satisfiable or not.
Okay.
The thing is that I will keep on generating the assignments, and quite possible that in the
you are generating them in, let's say, lexicographic order.
Yes. So
okay.
So in the worst case, I'll have to explore, say, exponentially large number of
exponentially large, yeah.
So that is how this P algorithm will work.
Yeah, but since you are exploring exponentially large number of them,
yes,
and at each point you are using the SAT algorithm for it, which runs in polynomial time. So you ask, this is your first assignment to x1 till xn, and you will ask this to the SAT solver, which runs in polynomial time, and then you ask to 0 0 0 0 1 and so on and so on so forth, and you'll keep asking to the SAT solver. In the worst case, you'll explore exponentially.
Yes, and at this point, SAT solver is not required, because to verify whether the solution is a valid solution or not, how much time would I be required?
Exactly. You just need polynomial space. So anyway, this is a circuit value problem. You can evaluate it without SAT solver.
Okay.
Right, but you get why we cannot use a this non-determinism directly, right? We cannot use non-determinism directly. We cannot say we are guessing now, because in a deterministic setting it does not make sense.
Yes.
Right. Okay. Good. But the now yeah, Suraj has already given this answer. Okay. And but this and I'll build on it. Okay. I'll build on this only. So okay, good. So there are exponentially many possibilities, right?
Yes.
And I somehow need to use SAT to guide me to the correct answer. So here's what we do. We can put value in variable and run P algo for SAT and check is that value leading to satisfying. If not, we'll put another value in second variable. Repeat n times for n. Oh, okay. Wait, now that I read. Okay. Suraj, okay. So Suraj, your approach is, first I'll do x1 and the rest I'll keep as x2, x3 and so on till xn. Let's say the SAT says no, then I'll take x2 and I'll put here 0 and so on till xn. and then it will say, let's say yes, then I'll fix this value, then I'll go to x3 and so on. This is what you're saying, right, Suraj?
Sir, if it says no, then I will change x1 from 0 to 1 and then again run side.
Oh, okay. Then that's correct. That's right. Okay, good. So here is the nice thing about SAT. Okay, and so here's the algorithm. Here's the algorithm. I'll write the algorithm directly. Should I write it? No, I think drawing it is better. So here I have 5. Okay, and it has x1, x1, x2, x3, and so on till xn. Now at this point, I'll check whether this is satisfied. How? Using the SAT solver. That runs in polynomial time. Right? Now, let's say it said yes. If it said yes, okay, and let's say it said no, then I'll just reject. I'll output something like NA because I don't have any satisfying assignment. Okay. Sorry. Now what I'll do is I'll fix one of the variables, okay, to 0, and then ask, is this satisfiable? This is still a formula, although it has a fixed input also. It is still a formula, and I'll ask whether this is in SAT. Suppose it says no. Then I'll change the 0 to a 1. And then ask. Then of course this guy is in SAT because initially the formula was set to be satisfiable, and either x is to be set to 0 or 1. So on setting x to 0, it is not satisfying. Then obviously on setting x to 1 is satisfying. So I don't even need to bother checking whether it is in SAT. So next what I'll do is, I have two possibilities now. I'll change phi to 1 and 0. I'll change x2 to 0 and x3 and so on till x. Or I can have phi 1, 0, x3, okay, not 0 this time, 1, x3, so on till x. Now again I ask if this guy is in SAT. And let's say it says no. Then obviously I'll fix it to 1 and then ask the question again. Right. So at the end, you can see it needs like an inductive argument for it, but you can see that at the end, okay, and at every level, it is answering me the correct answer, okay, whether it is satisfiable or not. And every time at each point, I'm fixing one of the inputs. What is the height of this tree? At the end, I'll get a phi 1, 0, 1, 1, sorry, 1, comma, 1, comma, 0, comma, and so on till. So this is a satisfying assignment. I get that. And at every level, I'm fixing one input. How many levels do I have? N levels. N levels. Yeah.
I have a question here that how did we get the first yes? So what's the meaning of first yes in this tree?
Exactly. So this is using the SAT solver. Okay. The first yes says, yes, you can explore ahead. There is a satisfying assignment.
Oh, I see.
Okay.
So SAT solver means that at this point, a very powerful algorithm, say, just because that P is equal to NP. So
because P equals NP. Yeah.
Just P is equal to NP, we could at least predict that this Boolean formula is satisfiable.
Exactly.
And now it is a matter of getting the values of the Boolean network.
Right. Right.
I see. Yes.
Okay. So if it says and then I fix, okay, if it says yes, there exists an input assignment that satisfies, then it is worth exploring. Then I continue. If it says no, then it's not worth exploring anyway. And then it's just a matter of fixing each variable one by one, and then accordingly using the SAT solver. Okay. And at each point, I'll use at each level use m once, and plus m runs in polynomial time. So time taken is n level times the time taken by machine m, which is n times some polynomial, which is still polynomial. Okay.
So what will be the height of this tree?
The height of this tree will be n. Why? Because at each level it will be n, because at each level I'm fixing at most one input.
Yes.
Exactly one input, and there are n inputs to the formula.
Yes.
Right? Okay, so that will be the height of the tree, and therefore we obtain at the end we'll be fixing n values, and that will be our. So this is the answer, and this is a special property of satisfiability. It is this is a property that was a peculiar property about some few languages, and this is what is called self-reducibility. That SAT reduces to SAT itself. Okay, SAT reduces to a smaller instance of SAT. So this is called the self-reducibility property of SAT, and in fact, this kind of a particular reducibility is what is called downward self-reducibility. Okay, of SAT. Anyway, and even currently there are softwares, there are programs called SAT solvers that aims in finding SAT solvers, finding very efficient SAT solvers despite the P versus NP hurdle. It's used in program verification and so on, all over the place. Now, actually, why I gave this question was to firstly because of the self-reducibility, which is a nice thing to know, and secondly to prove this theorem. Okay. But we don't have enough time. I'll do something else right now. But please try this. Please try this and use downward self-reducibility. Okay.
So the in the other book which you suggested, the nature of computation by Chris Moore.
Right.
So in that book, in the satisfiability, I mean, in the chapter where he explains satisfiability, so he talks about that tipping point thing that I mean, initially the Boolean formula or the satisfiability problem is not that difficult, but beyond a point it becomes very difficult. And then he has made some calculations related to the density of the Boolean formula and not many other things also.
Yeah.
So would it be possible for you to, in the next section probably, that you explain that thing in half an hour, that I mean this satisfiability problem, the different aspects of the satisfiability problem related to the density of the Boolean formula and the tipping point phenomena, that stuff.
Okay, sure. I'll just keep a reminder. Okay. For the next session, just keep a reminder because I might forget. Yeah. Okay. Yeah. Sure thing. And we'll be moving on to the realm of Boolean functions anyway during the coming weeks. Okay. Because now we are slowly moving on to circuit complexity, right? And so yeah, I'll be happy. Oh, okay. Thank you. Okay. Sure. We'll do that. Okay, so please try this exercise. I'm sorry I have to leave a bit early today. I shall be viewing recording later. Yeah, that is fine. Okay. Okay. Okay, so this is another thing I want you to try. Okay, this is another exercise. So here I'm defining a variant of matrix multiplication called Boolean matrix multiplication. Okay, instead of multiplication and addition, sorry, multiplication of addition, we are doing ORs and ANDs. Okay, question is, can you use ORs and ANDs to actually prove Savage's theorem? Okay, use Boolean matrix multiplication to prove Savage's theorem. So this is another one thing I want you guys to try. So moving on, yeah, let's quickly go to circuit complexity. Okay, so and we'll quickly wrap up this session. Circuit complexity. Okay, because it is just an introduction. This week's content has just an introduction to circuit complexity. It's not very dense, so I'm just doing a simple question here. Okay. Circuit complexity. Okay, formula can be written as or a formula can be written as follows, right? As we already saw. And so on. So this is a formula. So I can write it as an expression, but I can write it as a tree. Now, circuit is not a tree. In a circuit, I can have multiple output to each gate. Okay. For example, this is a formula. For example, this is a formula. In a circuit, I can have something like this is allowed. Multiple outputs. This OR gate is feeding both to the OR gates above it. Okay. And this is feeding here. And yeah, let's say it can do it very arbitrarily. Okay. So formulas, circuits are circuits are seemingly more powerful than formulas. Much more. Actually, circuits are definitely more powerful than formulas. Okay, in computation, because you are allowed to, take these wires several times and so on. Okay, and so now the question, okay, multiple output to each gate. So it forms a graph instead of a tree. In other words, okay, and why study circuit complexity? Well, it's a hot topic right now for quite some time, and it was used. We'll see in the next week's lecture, but it was used extensively to try and approach the P versus NP problem. So it was believed that using circuit theoretic results, you can actually separate P and NP. Okay, but that hope seems to be a bit far. Okay. But there are several applications of circuit complexity which you will be seeing in the coming lectures, so I don't want to spoil that for you. But here is a simple question. Okay, the fan-in of a circuit is the number of inputs to each gate in the circuit. Okay, for example, this gate has fan-in 2, this gate has fan-in 3. Okay, show that any Boolean circuit over AND or NOT with fan-in k, okay, which is greater than 2, and the circuit is of depth d. What is the depth? Depth is the longest root to leaf path in the circuit. Okay, from the output gate to the inputs. Okay, what is the longest path? And can be converted to one with fan-in 2 and depth at most order of d. So what it is saying is, if I have a circuit which looks like this, and let's say it It looks something like this. Observe that this gate has fanning 3. I can convert it into a 1 where all of them have fanning 2, where all the gates have fanning 2. So Suraj, you are saying dummy nodes. Okay. In what sense? Can you be slightly more descriptive?
Means we can make some extra gates which will be only attached to two inputs, and the third input will be connected to the output of the dummy gate.
Okay. So let's say this AND gate has 6. Okay, let's say 4. Let's say it has 4 inputs. I can convert it into, yeah, continue. What do I do?
We can make two input to one AND gate, and then
Okay. And
then one more input to output of that AND gate.
one more input to the output of that AND gate.
Means one more line will be there, and we will do AND.
Okay. So you mean this. What do you mean this? Sorry.
No, sir. It will be like tree-like structure.
Oh, it will be a tree-like structure. Okay. Okay. So you have an AND gate with 2 inputs. Now, okay. So here you want to put an AND gate, you mean?
Yes, sir, like this.
Okay, you put an AND gate here, and this will have 2 inputs,
Yes, sir.
and then
Uh, one more AND gate at the end.
here.
Hmm.
Right. Good. Yeah, that's correct. Why is this the case? Because so every AND gate, okay, you convert it to a 1 with this, and this will have all the AND gates here have 2 inputs. So the fan in is 2, and you do the same for OR gates also. Yeah. Why? Because this is possible by associativity of and OR. So that is A and B and C can be done in any order. So it does not matter for and OR. So this is possible by associativity. Good. So it can be converted. And why is depth at most D? Because um, yeah. So if I have any AND gate, it has, say, this time 8 inputs. I'll convert it into it turns into a binary tree with 8 inputs. Converted to binary tree with 8 inputs. And depth, what is depth? Log of 8, right? Which is 3. Turns into a depth 3 circuit. So any K fan-in circuit is converted to not circuit, gate is converted to a circuit of depth log K. Okay, any K fan-in gate is converted to a circuit of depth log K, and if there are so depth of circuit of the entire circuit is D, which means the number of gates in each path is at most D. So new depth, okay, on, so if this is your circuit with gates here, and I replace it with a log K gate here in each of these, so it will be at most log K times D, which is order of T, if K is constant. Okay. So this argument for us. Okay, that is now one final question. Okay, now similar question, but this is about fan out. The fan out of a circuit is the number of inputs to each gate in that circuit. Number of outputs, sorry. Show that Boolean circuit with fan out K is greater than 2 and depth D can be converted to a fan out 2 and depth at most order. Okay, so if my circuit looks like this, then I can convert it into gates with fan out only 2. Any idea, Suraj? Fan out this time.
So same thing we can do. We will make a tree and we will repeat the AND gate with two inputs.
But now the I'm increasing the number of, okay. So I have this AND gate. Okay, and now I do this. For OR it will work. Okay. For AND, let's try. Let's do AND between two variables x and y. Okay, and you mean this, right, Suraj? Oh, sorry, not AND, or AND. So question is, what will I give as inputs here?
Sir, in leaves we can give output input as x and y.
In leaves we can give, but we are increasing the number of inputs. Okay, but in other words, we can do this, you are saying, right? Connect extra wires.
Yes.
And if you are doing AND here further, then you are connecting extra wires here, which will not be a problem for us, because again it is associative. So once you do x and y, and if you do and x again, so it will just be x and y. So yeah, this is correct. Okay, another way to do it is, if you do this, okay, and you AND it with ones, and here also you AND it with ones. This will also give you the same result, because if the AND gate outputted a 1, then the 1s will match. Otherwise, if it's a 0, then since we are doing it over AND, then despite ANDing over 1s, we'll still get it. Okay, so and you can try the same thing for OR. If you have this, then do this. set one of the inputs to 0, and so on. But yeah, so this is about the fan in and fan out, and we can use the same depth argument to show that the depth is at most orderly. Okay, and I think that is it. Now, question is, what is the formula? Formula is a fan out 1. Okay. So can I convert it? Can I do the same question fan out 1 instead of fan out 2? Can I use the same technique to convert it into a fan out 2 circuit? Suppose this was fan out 1 circuit. Because fan out 1 circuit simply means a formula. One input, one gate's output is feeding to at most one gate's. Suraj, is my question clear?
Yes, sir.
Yeah. Will the same technique seem to be working? Okay. Should I?
Yes.
Yeah. Okay. So the answer is that it's not possible using this technique, because I think you've tried it and you observe that as soon as I have a fan out 1, there is no for copying this. I want to show this, that this is possible, but there is no hope of doing this unless what I do is I add more gates. And how many gates do I add? As many fan out there is. And here I'm adding lesser gates. Okay. And but so this is the reason why a formula, converting a circuit to a formula is not simple. In fact, when you convert a circuit to a formula, then you'll actually end up blowing up the size of the formula. So small formulas actually, so in the other way around, small formulas, okay, the other way around is large formulas can be brought down into small circuits, whereas small circuits can in turn turn into a large formula. So turning it into formulas and circuits have a large power gap in between. So circuits can do a lot compared to formulas. Okay, and just because the circuit can take one wire from one gate, it can take multiple wires outside from a single gate. The power of circuits increases a lot compared to formulas. But we'll see that soon. Okay, we'll take a dive into circuit complexity, and next lecture I'll also explain, although probably it will be done in lectures also, why circuit complexity is very relevant. Okay, and this is actually a great frontier in the current research scenario in complexity theory. So with that, we'll end this session. So if you have any questions, I'll stop the recording. Okay.